Hello, everybody. My name is Boris Botvinnik, and I would like to present a joint work with Jonathan Rosenberg on positive scalar curvature on spin C manifolds and manifolds with singularities. And this is the first part of presentation. The second part will be done by Jonathan. And in the beginning, I would like to say, though, that it is a great pleasure to be part of this workshop dedicated to Misha Gromov. And I would like to confess also that Misha is one of my mathematical heroes, and his work certainly changed my viewpoint on mathematics and determined direction of my research. Now, I would like to start with motivation. So as we know that from the viewpoint of differential geometry, not all manifolds are quite equal, then manifolds have spin structure or they don't have spin structure. And several fundamental questions are very different, have different answers and different level of difficulties if we, in the case of spin manifolds and non-spin manifolds. It's easy to check that that manifold is spin or non-spin. Indeed, manifold M is spin if oriented manifold, compact oriented manifold is spin if the second Stiefel-Whitney class is equal to 0. Now we recall the fundamental result due to Gromov-Lawson from 1979, which says the following: if manifold M is a compact non-spin manifold of dimension at least 5 and simply connected, then M always admits a positive scalar curvature metric. So it is quite important to and emphasize this, that we do not have any abstraction in this situation for the manifold to carry metric of positive scalar curvature. Now, as well as say if we have manifold with spin structure, then we know that such abstraction exists. We would like to consider a class of manifolds which is quite close to be spin and maybe as close as possible. And namely, we consider spin C manifolds which are not spin. This condition is also easy to verify. It is enough to check that second Stiefel-Whitney class is non-zero and find, if it is possible, to a class integral class in cohomology which maps to second Stiefel-Whitney class under the mod 2 reduction. Now, then also we know that such a class gives a map from manifold to CP infinity, which is, by the way, is a Ellenberg-MacLane space KZ2, which classifies all cohomology elements in dimension 2, in integral cohomology elements in degree 2. Then what we can do, we can take a Hopf bundle over CP infinity and take it back over manifold M. So, and then this complex line bundle actually carries all information about spin C structure on M, and we would like to keep this notation that M, pair M and complex line bundle is a spin C manifold. L emphasizes the choice of the spin C structure. Then what we can do, we analyze a little bit more carefully this construction. So this map to CP infinity maps M to finite dimensional skeleton because manifold M is finitely dimensional. And so then what we can do, we can change a little bit C so that it becomes a transverse regular near CP k minus 1. And then this manifold B is a inverse image C minus 1 of CP k minus 1. And then also here we have that line bundle over L over M, if we restrict to B, is nothing but normal bundle of the embedding M to B to M, B to M. So this construction is well known in algebraic topology, and this manifold B is called dual to this complex line bundle L. Now, what else we would like to do? We would like to look at tubular neighborhood of B inside of M. So what's going on is that there is the same manifold B, and we look at tubular neighborhood, which is a submanifold of M, and it's a total space of the over B of fiber bundle with the fiber disk. And also we would like to notice that there is a boundary of this tubular neighborhood is a total space of the circle bundle over B. Okay, and then we put together this, so we have a decomposition of M into two pieces, X, which is M without tubular neighborhood of B, its interior, and so we glue together with this tubular neighborhood. Now, what is interesting, one can show quite easily that X is a spin manifold, and boundary also spin, and boundary has, as we already noticed, is a total space of the circle bundle, principal circle bundle over base B. And of course, the boundary of this tubular neighborhood has natural free circle action, and also the whole tubular neighborhood has circle action, which is free outside of zero section B. And this is the question we would like to analyze. Does there exist a metric, positive scalar curvature metric G on M, which with given decomposition such that the restriction of this metric to tubular neighborhood is S1 invariant? We give a special name to this metric G. We call it well-adapted positive scalar curvature metric on ML. In order to proceed, we have to clarify an important geometrical issue, and this is a result due to Berard-Bergy back in 1981. It turns out that this is not quite well-known result, as we discovered. So if we have a manifold Z together with free circle action, then there is a projection to the orbit space, which is a manifold Z over S1, and the theorem says that if Z admits S1 invariant positive scalar curvature metric, S1 invariant, if and only if the base B admits a positive scalar curvature metric. And in one direction, it's actually easy, but in other direction, it's more complicated. It requires some geometric analysis, like using conformal Laplacian and conformal deformation of the metric. and something like this. Now, I would like to give three examples which illustrate that the question that we ask is quite interesting. We start with the manifold K3 surface, and we know very well that K3 has several wonderful properties. In particular, it doesn't have positive scalar curvature, and it's actually simply connected, and it's spin. And it has also second cohomology has rank 22. If we choose any generator, then we have a corresponding map to CP infinity, and then we can take a circle bundle, pull back it for over CP infinity to this over K3, and we get a manifold Y5, Y of dimension 5, and it's not difficult. It's actually quite easy to show that this manifold, in this case, is simply connected. It's also spin, and it's a boundary of some manifold of dimension 6. Spin manifold of dimension 6. The reason behind that is that spin group in dimension 5 is 0. So every closed spin dimensional, 5-dimensional spin manifold is a boundary. Then, so what is interesting then, if we put together this X of dimension 6 and corresponding this bundle over K3, we get a manifold of dimension 6, which certainly has positive scalar curvature metric. However, manifold M6 doesn't have well-adapted positive scalar curvature metric, because otherwise it would be S1 invariant on Y5, and then it would give positive scalar curvature on K3, and this is what's going on. Second example is the following. We start with an exotic sphere, dimension 10, such that alpha invariant of this sphere is non-zero. In particular, it means that it doesn't admit a positive scalar curvature metric. Then, if we delete this a disk from this 10-dimensional exotic sphere, then we have a boundary which is a 9-dimensional ordinary sphere, and which has free circle action, namely S9 fibers over CP4, as we see, and then we denote by N CP4 over CP4 corresponding this bundle with this particular boundary is a 9-dimensional sphere, and obviously this bundle has a S1 invariant positive scalar curvature metric, is a standard one. However, no such metric extends to a well-adapted positive scalar curvature metric on the manifold M, which we put together from X and this bundle. Indeed, if it does extend, if it extends, then we have a positive scalar curvature metric on the original exotic sphere, since on S9 it has to be standard, and then we would give an extension to sigma 10 where there is no metric of positive scalar curvature. Okay, one more example. Then we start with the manifold B, which is our exotic sphere, together with the 5-dimensional CP5. And then this manifold is known as a fake complex projective space, and it also has a principal circle bundle over, and the total space of this is a exotic homotopy sphere, and alpha invariant of this is equal to 0. It's actually in 11-dimensional exotic sphere always admits a positive scalar curvature, and also it's a boundary because 11-dimensional spin group is also 0. And then, but manifold B doesn't have positive scalar curvature because alpha invariant of this manifold is non-zero. Then what happens is that if we put together our manifold, 12-dimensional manifold X, together with the tubular neighborhood of the of B, then this manifold has a positive scalar curvature metric, but it does not admit any well-adapted positive scalar curvature metric for any X, for any choice of X. Okay, so now let's analyze a little bit what we have. If we have a spin C manifold, then and this manifold has decomposition X and tubular neighborhood of B, and then we think about G, what is well-adapted metric. So not necessarily positive scalar curvature, but well-adapted metric gives we restricted on the tubular neighborhood, and it has to be a submersion metric on the tubular neighborhood, which is given by the metric, by some metric G sub B on B, and flat metric on the disk. And then we have several Dirac operators which possibly abstract to existence of well-adapted positive scalar curvature metric. Namely, we have a Dirac operator on manifold B, which is spin. Now, Dirac operator on twisted Dirac operator on the same B, which we twist by the bundle L, actually L restricted to B. And also we have a Dirac operator on X with IT-Patodi boundary condition on the boundary. And again, the metric on the boundary is determined by the metric on the base and the standard flat metric on the circle, because we have there Riemannian submersion del X over B with this circle as a fiber. Well, so let's see. If we assume that our metric, well-adapted metric, has positive scalar curvature, then in particular we have restrict on X, we have positive scalar curvature, restrict on the boundary, and also on submanifold B, we have also positive scalar curvature. Then what we see that the Dirac operator on B has to be invertible, because this is greater than 0. Then the manifold boundary del X is the total space of the circle bundle for some connection A. And then the scalar curvature is given by scalar curvature of the restriction on on the boundary is given by the scalar curvature of the metric on the base and the curvature of the connection A, which we choose. So this is S G restricted on del X is actually 1/4. This is then. So if this metric has positive scalar curvature, then this operator has to be invertible as well. Now then the last one, so then we have already metric on del X, this is X, and then this is G del X, we would like to extend to metric on X. Then there is a Dirac operator with a T-Patodi boundary condition on the boundary del X. And then we see that this operator has to be invertible as well. Now, so we combine these three with these Dirac operators and give index alpha S1 FB fiber singularities as valued in the K-theory, which is actually sum of three particular groups, real K-theory in degree n-2, which comes from the Dirac operator on B, this complex K-theory, which comes from the Dirac operator on B with a twisted L, and the other one is on X with a T-Patodi boundary condition. And then we have the following, theorem that theorem which we proved 2 years ago, that ML spin C manifold with corresponding decomposition as we see, and assume that M is simply connected and dimension M is at least 7. Then M admits a well-adapted positive scalar curvature metric if and only if this index is 0 in this group. Okay, there is one more result we have here, which is we look at ML, so spin C manifold, and of course it has its own Dirac operator, spin C Dirac operator del M, and which with the index which lives in complex K theory. And recall that if we choose a connection, excuse me, then we have a Lichnerovich formula that so which includes, of course, this curvature term of the connection A. And we say that this is, we call this part a twisted scalar curvature. And the result we have is the following. If we have a spin C manifold, which is not spin, then assume M is simply connected and dimension is at least 5. Then there exists a Riemannian metric G on M and the connection A on L on the line bundle such that twisted scalar curvature is positive if and only if this spin C index valued in complex K theory is 0. So I will conclude with the following note. So first of all, in this case, as we see, if we have spin C manifold, simply connected, dimension is 5, then according to a theorem that we cited in the beginning, M has always metric of positive scalar curvature. However, as we see, it does not necessarily have a metric with twisted positive scalar curvature. And this is example. Let's take Bott manifold and take a connected sum with CP4. And then we can verify that it's this manifold is spin C and not spin. And then so of course it has also a metrical positive scalar curvature. However, there is no metric G on M and a connection on A on LM such that twisted scalar curvature is positive. Thank you, and this is what I would like to share with you, and this is the end of the first part.